Okay, welcome to week 6. This is a pretty fun chapter in my opinion. We're going to get into some interesting and kind of challenging stuff here. So I want to give you some pointers for how to think about some of the physical systems that we'll be modeling here. Okay, so don't forget, in the past, up until now, we've thought about gravity as a constant vector, right, pointing straight down. Now we're going to think about gravity in a more sophisticated way. So think about the following case study here. Think about the Earth, okay, and think about a satellite, be it the moon or an actual satellite, out in circular orbit around the Earth. Okay? So don't forget about Newton's first law, that the satellite would remain with constant velocity, that it would point in this direction unless it were acted on by an external influence, in this case, a gravitational force. Now, also don't forget that in order for uniform circular motion, UCM, that the acceleration has to point radially inward, all right? And that acceleration has to have magnitude v squared over r. Now, in this case, both v and r are going to be constant, okay? We call this the centripetal acceleration. It points radially inward, okay? Now, the gravitational force has the following form, and I'm going to put it as a vector, okay? The force due to the Earth on the satellite is going to be some constant g times the mass of the Earth, the mass of the satellite divided by r squared. Now the tricky part that you have to think about here is that because it's a vector, it points. And I think you'll agree that in order to produce this acceleration, I need a force that also points radially inward. The force due to gravity. Now radially inward means it points in the minus, I call it r hat direction. It's the minus radial direction, okay? So this direction out this way is the radial direction. So I use r hat to mean radial direction, okay? So you're going to want to think about this because the gravitational force points radially inward all around the uniform circular motion path, okay? So look for implications of this motion. I encourage you to check out slide 660. Okay. One of the, I think, intuitive ways to think about this, hopefully you will as well. Think about this failed launch idea. Okay. So in this slide, so this is 646 in the chapter 6 presentations. We think about a projectile motion problem initially, right? First of all, we'd have a parabolic trajectory, okay? If we zoom out, what we're really seeing is that the gravity, the force due to gravity points towards the center of the Earth, regardless of where we are, okay? So we talk about projectile motion as failed orbital motion. That's an okay place to start. But what happens if we launch it with sufficient speed, okay? So in slide 647, we imagine launching the projectile, and when that speed is sufficiently large, okay, the acceleration the object experiences is exactly what it needs to produce this centripetal acceleration. All right, so if you look at this picture here, all around the circular motion, gravity points inward. That's exactly what's required to keep it in uniform circular motion. So when the centripetal acceleration is equal to g, then imagine the object in uniform circular motion just at the radius of the Earth. All right? So that's the thought experiment. Forget about air resistance, forget about anything else, right? The idea is that this constant here matches exactly what we would need for v squared over r. Okay? So, as you get into this problem, try to think about gravity in this new way. It's a new way of thinking about it. All right. And if you have a hard time doing this, come and chat with me. Okay.